All right, good morning, everyone. I'm Ben Sachs. For those of you who don't know me, I'm a C++ trainer. My company, Sachs & Associates, offers training for companies all over the world. And if you guys want to reach out to me later, there's my email address. Got a lot to get to, so let's just go ahead and dive in. All right, so at a very basic level, computer programs are made up of entities and actions that we perform on those entities. I'm using the term entity because as a generic thing to describe functions, namespaces, objects, templates, lots of different things that make up our program. Because we can have declarations for many of those different things. There are some entities that aren't declared, but many of them are. And when we declare something, the way that we declare it can give that name certain properties, like a type or a scope. Storage duration and linkage are a couple of others. Now, not every name has all of those properties. So objects, for example, int I, that has a scope, a type, storage duration, and linkage, depending on where we place that declaration and mainly where we place it. Whereas functions do not have a storage duration. There's no such thing as a function that doesn't take up, whose code doesn't live for the entire program. Even if it's a function like a lambda, the code exists for the duration of the whole program. Things like case labels for something like a goto, not that I'm suggesting you use gotos for anything, but just they are still part of the language and they are useful for demonstration purposes as showing those just have a scope. There's no type associated with them. They don't take up any storage, anything like that. Okay. There's a common source of confusion in the language is the distinction between declarations and definitions. So a declaration introduces a name into the program and provides the compiler with some information about the entity being declared. Not necessarily a complete set of information. And it just says this thing's going to exist somewhere in the program. Maybe here, maybe elsewhere. Whereas a definition gives the compiler, I should say, a complete set of information about the thing being defined, and also gives its location. It's right here where the definition is located. So all definitions are declarations, but there are declarations that are not definitions. So, for example, here we have a function declaration. It's not a definition because it doesn't have a function body. We don't see the brace enclosed body here. It tells us enough to know how to call the function. Again, I should say that it tells the compiler enough to know how to call the function. We know that it takes an int and returns an int, but there isn't any information here that the compiler can use to know, or there isn't enough information here to tell the compiler how to generate the code that will actually execute the body of the function. On the other hand, here, this is a definition for that function. We have the brace enclosed body, and this tells the compiler enough to actually generate the function, the code to execute when that function is called. When we talk about objects like int I there, int I is a definition. We have to go a little ways out of our way to get something that is actually a non-defining declaration for an object. We need to use the keyword extern, like in that middle example there. And we need to not provide an initializer for that value. The reason being that an object definition allocates storage. It tells the compiler, and by extension, the linker, where this object is going to be located at the place where the definition exists. And If we have an initializer, the only way that makes sense is if we know where that value is going to be stored. So this thing must be a definition. Whereas the middle statement there, extern int j, that doesn't allocate any storage. So a non-defining declaration introduces a name into the program, but it's a name that the thing that's being declared exists somewhere else, not here. Whereas a definition gives you the full set of information, which includes, and here it is. And I'm saying that the statement here applies to functions, it applies to classes and templates. Same distinction applies very broadly throughout the language. So let's talk a little bit about how declarations are structured. And I'm going to do this in a series of steps. Now, declarations can include initializers, as we just saw. I'm going to start off leaving the initializers out for the sake of keeping things simple, so we can, and then we will factor in the initializers a little later. So to start off, a declaration is made up basically of two parts. There are what we call the declaration specifiers, one or more of those, and then a declarator, which is the name being declared, possibly surrounded by operators. And we can have a sequence of declarators in a declaration as well. We can declare multiple things on one line, although often we're advised not to. The name being declared there, X, I'm going to call the declarator ID. That's a term from the grammar of the language. Although N there is part of the declarator, it's not being declared. N must exist, must have been declared somewhere before here. So a declaration specifier, we can further break those down into type specifiers and non-type specifiers. So type specifiers, they can be keywords like int or unsigned, long, double, etc. Or they can be the names of user-defined types like string. Again, string we usually think of as coming from a library, but from the perspective of the language, it's still considered a user-defined type because it's not built in. And template specializations, like a vector of long doubles. That's a type specifier. A non-type specifier, there are a few different kinds of these things. There are storage class specifiers like extern or static. There are function specifiers like inline or virtual. And then there are a few other things like friend and typedef that are sort of occupy this other category, a miscellaneous kind of thing. So the declarator is made up of the declarator ID and then possibly some additional operators. And those operators mean various things. Star for pointer, single ampersand for L-value reference, what we used to call just references, double ampersand for R-value reference, square brackets for array, and parentheses for function. Although, as we'll see, parentheses can actually mean two different things in declarations. They can mean function, they can indicate a function, but they can also indicate grouping. So here, let's go ahead and break down this declaration here. Starting with the declarator, this says that X is an array of n elements of type pointer to something. And the something is being determined by the declaration specifiers, the static unsigned long int. But just the declarator just tells us X is an array of n pointers to something. Now, static is not actually part of the type. It's a declaration specifier, but it doesn't really contribute to the type of X, it provides other information about what X is. Those other properties that I talked about earlier, like storage duration and linkage. Now, how do we know that X is an array of pointers? Couldn't it be a pointer to an array? We don't see pointers to arrays all that often, but they do exist in the language. You can write them. So, given that declarator, how does the compiler know that that means array of pointers, that that was what I had in mind? Well, the rule is actually fairly simple. The operators in a declarator follow the same precedence order that they do when they appear elsewhere in the language. So as I mentioned, parentheses have a dual meaning here. They can be used for grouping, and we'll see some examples of that in just a moment. They can also mean, as grouping, they have the highest precedence of all. The square bracket and parentheses that indicates function then are at the next level, and below that we have pointer, lvalue reference, and rvalue reference. And so this is an array of pointers because the square bracket has a higher precedence than the star. So it takes effect first. X is first an array. An array of what? An array of pointers. Now, parentheses, as I mentioned, can play two roles here. There's the function call operator, and these follow the declarator ID. When I'm declaring a function, the parentheses occur after the name being declared. They don't contain it. And in that case, they have the same precedence as the square brackets. Grouping parentheses enclose the name being declared. And they have the highest precedence of all, and they exist because they're generally used when we want to take one of those lower precedence operators and make it group more closely than one of the higher precedence operators. So for example, here, f is a function that takes an int and returns a pointer to something as given by the declaration specifiers off to the left. Again, the parentheses here have a higher precedence than the star, so they take effect first. Whereas here, I've introduced some grouping parens around the star f. So now the star will take effect first. And f here is a pointer to a function that takes an int and returns something. This is why when you write a pointer to a function, you have to write those parens there. Otherwise, it means something different. Now, I can put in parentheses there unnecessarily. The compiler will just ignore them there. They're just surrounding f, so they have no real effect. F is still a function that takes a parameter of type int, returns a pointer to something. But this can help. We don't typically do this intentionally, but occasionally it's something that we do by accident. And that can be, this is the source of what we sometimes call the most vexing parse error, as Scott Myers referred to it. Now, we can have much simpler declarations. Even that int n there, that has a declaration specifier and a declarator. N is the full declarator. It's just the name being declared. And things can be as simple as that. Now, the type specifiers, type and non-type specifiers behave a little differently. The type specifiers all get combined together, and they collectively determine the type of the thing being declared. Whereas the non-type specifiers, I think it makes more sense to think of them as applying directly to the name being declared. So unsigned, long, and int are all type specifiers. They describe the thing that the pointers in X point to. Whereas static provides information that applies directly to X rather than being part of the type. So Another thing that's interesting here, the order of the declaration specifiers doesn't matter. I think I usually see people write unsigned long, for example, but you can write long unsigned. And it means the same thing as far as the compiler is concerned. Your coworkers might not agree with it, but for the compiler, it doesn't matter. So same thing here. However, I order those three type specifiers. Those are all declaring the same kind of thing in C++. Now, const is a type specifier. This is something that people sometimes get confused about. It mixes in with the other type specifiers. So v there is being declared as an array of n pointers to constant integers. It's not that v itself is constant. It's that the things that the pointers point to must be treated as const. So this is a source of confusion for some people, but const is considered to be a type specifier. Now, const and volatile are sort of unusual in that they're the only symbols in C++ that can appear either as declaration specifiers or as part of the declarator. So there, again, order of declaration specifiers doesn't matter to the compiler. Those two declarations both mean the same thing. Array of n pointers to integers that are const. Whereas here, const is part of the declarator. It's on the right-hand side of the star. And now the const is modifying the pointer. This is an array of n constant pointers to integers, which are non-const. So a const appearing to the immediate right of a star declares something that really is a constant pointer. That is, where it points is fixed at the time of defining the object. The things that it points to are not necessarily const, but we can't change the memory address that the pointer points to. And I think that there's only one way to write these things. I mean, I guess I can write them all in there's only one real way to write this pointer. I can't reorder any part of that. And pointers are kind of unusual, along with references, in that you can think of them as reading from right to left. CPW is a constant pointer to a widget. Here. PCPW is a pointer to a constant pointer to a widget. And here, CPW is a constant pointer to a widget. I think it's a rule that scales up relatively nicely. And if I want to declare those things, that's how I have to declare them. Now, technically, the star and the const are separate tokens. The compiler doesn't care how I space things around there. But when it processes them, the compiler essentially combines them together into the const pointer operator. It has the same precedence as a plain star would in a declarator. Now, I'm realizing suddenly that I forgot my East Const armband here. Because I am going to take a moment to advocate for why I think that makes the East Const style makes things easier to understand. I think that the easiest way to make sense out of declarations involving const or volatile is first go ahead and write the declaration leaving out the const and volatile. And then, simple rule, put const or volatile to the immediate right of whatever it is that you want those terms to modify. So if we want x to be an array of n constant pointers to volatile uint32s. We can start by just writing it as array of n pointers to uint32, like that. And then we can go ahead and add in, and then here, same declaration, I've just added space for the CV qualifiers that I'm about to add in. We want the pointer to be constant, the pointers, I should say, since it's an array, to be constant. So we add the const to the immediate right of the star there. And then the things that they point to are meant to be volatile. So uint32t volatile star const x square bracket n. I tend to think that that's a fairly simple rule for knowing how to structure these declarations. Now, in some ways, it's easy for me to say that. Yeah, if you have a lot of code that's written in a different style, in the const west style, yeah, I'm not necessarily saying you have to change everything tomorrow. But I think that that at least helps clarify what the meaning is, even if you continue to write things in the other style. Okay, so now adding in the initializers like I said I would earlier. The initializer for a declaration can appear in a few different ways. We can write the equals initializer for what is sometimes called copy initialization, although it's not necessarily making a copy there. We have the parenthesized initializer, what's termed direct initialization, and then we have the braces for braced initialization. Now, declarations can declare more than one thing. We can declare more than one thing on the same line. Again, often we don't. But the language does let us do this, and it's worth knowing at least a little bit about how the language makes sense out of that. The rule is each of the declarators is separate. The declaration specifiers, the things off to the left, those are shared between them. But each declarator is treated independently, and they can have an initializer or they can not have an initializer. So here, f is declared as a function with a parameter of type int that returns the thing designated by the shared declaration specifiers, which here is just int. N is an object of type int being initialized with the value 42 using the equals sign form of initialization. And here p is an object of type pointer to int, because it's got the star in it, being initialized with the address of n. This is one of the reasons why people often separate things out onto multiple lines, is because the idea that this is actually declaring three things of three different types, something that a lot of people find confusing. And I don't know that, and I can understand why. And it's my job to know this stuff, so it's, but for those of us who have to, get the release out on Friday, we have other things to worry about. Okay, talking about const and Constexpr here. So I mentioned before that these are equivalent. Whether I write them in the order const char or char const, these two declarations mean the same thing. Now, Constexpr is also a declaration specifier, and again, since the order of declaration specifiers doesn't matter to the compiler, whether I write it as Constexpr char star p or char Constexpr star p, compiler doesn't care. Most of us write the Constexpr on the left, and including me, even though I typically use the East const style, and there's a reason for that, which is that these are not equivalent. This is something that can come as a surprise to people. Const and Constexpr have different semantics in this sense. A pointer that's declared Constexpr is really more like a const pointer than it is like a pointer to const. Here, in both of these cases, the thing that P points to is non-modifiable. It's always going to point to the same location, but the value at that location, we can use P to change it. So now the requirements on how we initialize these things are a little bit different. Constexpr has slightly more stringent requirements. So Constexpr is not really a type specifier. It's a declaration specifier, but it's not a type specifier. It behaves more like the non-type specifiers like static. And typically we place those far off to the left. So that's what I tend to recommend doing as well. Again, we think of it more as if it's modifying X directly than contributing to the type of X and getting mixed in with the others. So here, X is the Constexpr declaration, excuse me. The Constexpr declaration is more or less equivalent to the the array of const pointers declaration down at the bottom, with the additional requirement that the initializer for the Constexpr expression needs to be a compile time constant expression. Constexpr requires that the initializer be known at compile time, whereas things that are simply const, the initializer can be an expression that resolves at runtime. Okay. So the keyword type name has a few different places that we can use it in the language. I tend to prefer to write my templates like this, where I declare the type parameters using the keyword type name. So template, type name T, type name P, class widget. Now here, I could use the keyword class there instead. That's what I get for talking about const for the last 10 minutes. You start going on autopilot. Yeah. You can use the keyword class there to declare T and P in template parameter lists. In this place, class and type name are interchangeable. There's another use for type name where only type name will do. And that's what I'm about to explain here. All right, so the compiler processes templates in two phases, as we say. The very first time that the compiler sees a template like this, when it's just encountering the declaration of, here we have a function template, it doesn't know what T is going to be yet. In fact, if we've written this as a function template, probably it's because T is going to be several different things, and we expect to have several different versions of this function generated from the template throughout the program. In any case, the compiler, upon seeing this, doesn't know what T is going to be yet, so it can't generate the code for the function foo, even though what we're seeing here is the body of a function template. Without knowing what T is, the compiler can't generate the code for that body. Now, the compiler still tries to do some error checking during that first phase when it's reading through the definition of the function template here. It tries to do as much as it can to report errors during that first phase as possible. And then later on, the second phase occurs when the compiler actually encounters a call to that function template. at which point the compiler deduces the type from the function argument, or the type could be explicitly specified. Either way, that's when the second phase of template translation occurs, because now the compiler knows what the type argument for t will be. It can go ahead and substitute that into the body of the function and finish out doing the rest of the semantic analysis as part of generating the code for that specific version of the function template. So the first phase is when the compiler parses the template declaration itself, and that happens once, whereas the second phase occurs when the compiler is actually instantiating the template for a specific template argument or set of template arguments, if we're talking about something that has multiple template arguments. And that can happen several times, because in the program we can have several different places where we instantiate the template. So understanding that two-phase translation approach is the basis for why the keyword type name is required in some places in C++. So the standard library container class container types like string, well, string is considered a container, although we don't usually, often we think of vector, list, map, etc., but string actually counts as well. All of those container types have member types that they declare inside themselves, and some of them also have member constants. So all of the container types, for example, declare a nested type called size type. Usually it's an alias for something like size t. The string class template, string is actually an instantiation of an underlying template called basic string, as you may have seen in error messages. String has a nested constant called npos, represents the sort of a location where the location when we searched for something and couldn't find it in a string. We need the keyword type name when we're using the member types like size type in a template context. So here, this is a first attempt at writing a template. And I've left out the keyword type name here, and we're going to see why that turns out to be necessary when writing this code. So the idea here behind the munge function is that T is meant to be some string, a string or some string-like type that has a size type, member type, and an npos member constant in this situation. So this template expects both of those things to be properties of T. But again, the compiler only knows what T is during that second phase of template translation. It won't know that the first time that during the first phase of translation, all it knows is that T represents a type. It can't see what T is going to be, so it can't see what T : size type and T : npos are going to be at that point either. And without knowing those things, the compiler can't tell that T : size type is meant to be a type, whereas npos is meant to be a constant. That information only becomes available during the second phase of template translation. So let's think about, what does that line of code represent? How does the meaning of that line of code change there, depending on whether or not size type and npos are both types or something else? So if they're both types, what is that statement saying? It's a function declaration. because I is the name of the function. It's a function that takes a parameter of type npos, where npos is a member type of t, and returns back a pointer to a size type, the size type that belongs to t. That's if they're both types. Now, if size type is a type, and npos is something other than a type, a constant, object, function, something like that, which is the situation that we originally had in mind here when we or whoever it was wrote the munge function, then this is an object definition. We're creating an object called I with the value npos, being initialized with the value npos of type pointer to t : size type. Now, if neither one of them is a type, what do we have then? It's a multiply expression, I guess. I mean, there's a good chance that that doesn't compile at all, depending on exactly what non-type things npos and size type are. Even if it is a multiply expression, it's probably not very useful because usually we don't multiply things and then just do nothing with the result. But the compiler would be willing to accept that would be willing to read that if both of those things were non-types as, okay, well, I is the name of a function that's being invoked and being passed the value npos as the right argument, as the right operand of a multiply, where size type is the left operand of the multiply. I say I could be a function. It could also be a function like cast, something like that. So the meaning of that line of code changes depending on whether or not size type and npos are types or not. So in order to make sense out of that line during the first phase of template translation, in order to do the kinds of error checking that we want the compiler to be able to do during the first phase of translation, the compiler needs to know whether those dependent names, as we call them, the idea is that the values, the meanings of size type and npos depend on what t ultimately turns out to be. Those dependent names might mean something different each time the template is instantiated. Theoretically, there's nothing that prevents me from writing that code in such a way that theoretically, if not for the keyword type name, I could write that code so that sometimes that comes out to be an object declaration, and sometimes it's a function declaration, and so forth. And whereas names like other names in the function template munge are non-dependent names. Those are names that mean the same thing in every function, every instantiation of the function. Whereas dependent names, those are going to depend on what gets substituted in for t. So in order to make sense out of that munge function, the compiler needs to know whether something like t : size type is a type name or something else. And all that really matters is whether it's a type name or something else. Doesn't care if the compiler knows it's not a type name, then it'll figure out the rest of the details during the second phase of template translation. But it's important for the kinds of error checking that we want the system to be able to do, that we want the compiler to give us, to know whether something is a type name or not. Because type names, knowing that something is a type name, makes it clear that we're declaring something, can make the difference between declaring something and writing something like a multiply expression. So a name in a template declaration that is dependent on a template parameter. So when we have a dependent name, it's assumed not to name a type unless we explicitly say that it's a type by qualifying it with the keyword type name. So the assumption is that something that like t::size type or t::npos is not a type, and we have to explicitly say if it is. So if we want to write our munge function the way that we'd originally intended, we have to use the keyword type name in those two places, preceding the two uses of t::size type to make it clear that that's meant to be the name of a type, whereas t::npos, that's the name of, we're thinking about it as a constant, but it could be a static data member or something else. Either way, we know that thing is declaring something called I, because we know that size type is a type name. So on line 1 there, the keyword, we're using the keyword type name. That's a place where we could be using the keyword class instead. That's telling the compiler that that template parameter is a type argument as opposed to some non-type argument. Whereas on lines 2 and 3, the keyword type name there is making it clear that we intend for t::size type to be considered a type name. So we can substitute the keyword class on line 1, but not on lines 2 and 3. Only type name will do there. Okay. Last section. There's this, I mentioned before that the double ampersand in a declarator usually means rvalue reference. Before I said it means rvalue reference. Now I'm going to qualify that statement a little bit. In a declaration like the doit function there, arg is being declared as an rvalue reference to a string. And an rvalue reference has to bind to an rvalue. So the strings s1 and s2 there are L values. They're long-lived objects that have locations in memory where they live for the duration of time that they're that's associated with their definition. So I would not be able to call doit and pass simply s1 in, but s1 plus s2, that's an expression that yields an r value. I can go ahead and call doit on s1 plus s2. However, there are some cases where the unary double ampersand in a declarator means forwarding reference rather than rvalue reference. And this is a term that that's used in the standard. So here, in this template declaration, arg is being declared to be a forwarding reference to a t, rather than an rvalue reference to a t. Unlike an rvalue reference, a forwarding reference can bind to either an L value or an R value. So we use forwarding references. The name forwarding reference comes from the fact that they're often used to write what we call forwarding functions. Functions that take their arguments and pass them along directly to another function, maybe one of several functions, depending on what the forwarding function is doing. The idea is that the forwarding function, forwards its arguments along to someone else, the same way that you might forward an email to someone. Now, a forwarding reference conceptually remembers whether it's bound to an L value or to an R value. The reason that we use a forwarding reference like this is because we want to preserve the information about whether the thing that was passed in to the first function, the forwarding function, is an L value or an R value, so that we can forward that information along by calling to the function that it's being called, the forwarded to function, using the stood forward helper function. Yes, I know that I'm saying the word forward an awful lot here. I apologize, but it's a bit of a necessity to pass that knowledge along, because the function that we are forwarding to, knowing whether something is an L value or an R value, can be important for performing certain kinds of optimizations, like whether or not we can safely use move semantics. That's the case only if we have something that's really an R value. Then it becomes safe to move from. So looking back at this example, I said that arg is a forwarding reference here. Now, it's a forwarding reference rather than an R value reference because it fits two criteria. It doesn't have any CV qualifiers. It's not declared const or volatile. The rule is if it's got a const or volatile in it, can't be a forwarding reference. Must be an R value reference at that point. The second rule is that arg appears in a deduction context. And that makes it possible for it to be a forwarding reference. So the type T on that line is something that may be deduced based on the argument passed to dispatch. That's also a necessary condition for this to be for arg to be a forwarding reference here. So, as I said, a forwarding reference can't be const or volatile. So, for example, here arg1 is a forwarding reference, but similar declaration that includes the word const in the declaration of arg2, that is an R value reference, always. Specifically, it's an R value reference to const. We don't often use R value references to const. They're not terribly helpful. Usually, the reason that we want an R value reference is because we want to identify something as an R value so that we can safely move from it, and we can't move from something that's const, but the language does allow you to write them. And if we were to write this, we'd be saying specifically that arg2 is an R value reference to const. And then as I mentioned, forwarding references something is only a forwarding reference if it appears in what we call a deduction context. So arg, in the function dispatch that I showed you earlier, the T on that line of code can be deduced from a template argument depending on how dispatch is being called. So if I pass 3 to dispatch, the type T is deduced to be int. If I pass in 3.5, the type is deduced to be double instead. So that's what I mean when I say a deduction context. Now, it's easy to think that that means, okay, if it's in a template, it's a deduction context, but that's not necessarily the case. Here we have a line that's inside the function template that looks similar. But here, although arg is a forwarding reference, temp is an R value reference because it doesn't appear in a deduction context. The argument for T, the type argument, was set when dispatch was called by the way that the function was called from the outside. Inside the function, the code in there is not going to do anything to change the meaning of T. So once we know what arg is is a reference to, we know that temp is an R value reference to that same kind of thing. Similarly, here we have a class template that has a member function that takes, in this case, an rvalue reference. And it's an rvalue reference because the type argument for t there is set when we create the object of, oh dear. My computer just crashed on me here, apparently. Okay. Yeah, it's rebooting. It should be back up in just a moment. But as I was saying, the type argument there, when we are talking about a class template, the type argument is set when we create the object of that class type, by instantiating that class template. So I had a class type C that was, sorry. Thank you for bearing with me here. I think that's like the second time this computer has ever crashed. It's not that, so of course it happens here. Yeah, so here, when I create that object little c, that's where t gets locked in as being int. Regardless of what I pass to a call to c.mf, t is int. It was set when I created little c there. So that function is going to accept an rvalue reference to an int. Always. Now, a deduction context doesn't necessarily have to be inside a template. A declaration that uses the keyword auto also establishes a deduction context. So these can appear outside of templates. They still create deduction contexts. R1 is an rvalue reference to an int, whereas R2 is an rvalue reference to a double. These could also appear inside templates, and they would also establish a deduction context if they appeared inside a template. Wherever they appear, it's a deduction context. Okay, that brings me to the end. So now I'm happy to take questions if anyone has them.
Great talk. I was wondering in which cases, if any, does const applied to a Constexpr applied to a variable imply either const or static?
In what cases does it imply const or static when you declare something to be Constexpr?
Yeah.
So it's I'm scrolling back here to where I was talking about Constexpr because I'm so if I tried to add in I suppose I'm not entirely sure what you mean to some extent. So I could add, so I could declare, because those top two are not equivalent, I could declare something to be char Constexpr, to be Constexpr char const star p, if I wanted to. The const wouldn't be redundant there, because what I would be declaring would be, I'd be saying that the pointer is Constexpr. It's always going to point to the same location, and the initializer for that expression needs to be a compile time constant expression, and then the const would apply to the type being pointed to. It would be saying that the character that the pointer points to, I don't have permission to change it. Whereas there'd be no need in the writing something like Constexpr char star const p, adding the Constexpr to the bottom line there would be redundant. So I can't think of a case.
If you leave pointers aside,
Yeah.
is either const or static ever not redundant coupled with Constexpr?
I don't. When you have something that's is static, not redundant, there are lots of different uses of the keyword static. So I'm tempted to say that there are certainly places where if you don't use the keyword static, the compiler just won't make sense out of something. Like you can't have a Constexpr data member of a class type that is not static. The keywords, you'd be required to add the keyword static there. It wouldn't simply be implied by the presence of the Constexpr. Does that answer your question?
And as to const, is it ever not redundant?
Is the const ever not redundant? And you're saying if we're not talking about pointers or multi-level types. I can't think of a case where it's not. I guess I would say that there's. It's worth noting that there's a difference between a Constexpr member function and a const member function. Originally in C++ 11, Constexpr member functions were implicitly const member functions, but they changed that rule when we went to C++ 14. So you can have Constexpr member functions that theoretically return something that's a compile time constant expression, but don't promise not to modify the thing on which they are called. It's not that common, but it happens. I guess that's the situation that I can think of that most resembles the const and the Constexpr not being redundant there.
But neither case which revolves around variables rather than functions.
No, I don't. For a variable, I can't think of a case where, or for an object, I can't think of a case where declaring something, you'd need to declare something both const and Constexpr. Yeah.
We have a question online. When using auto ampersand ampersand, can an L value be passed to an R value?
Can an L value be passed to an R value when using auto ampersand ampersand? So what you're referring to here is on the last slide, I showed that you can write this. Oh yeah, sorry. This is not being. I showed that you can write this. And you're saying. Can I write this as well? And yes, I can. That is also valid in C++. And this is because, again, what I'm declaring here, R1 and R2 are forwarding references. So they can bind to either L values or R values, and they follow a rule called reference collapsing, where R2 will essentially be an L value, will wind up being something very akin to an L value reference to an int, whereas R1 will wind up being very much akin to an rvalue reference to an int. And that's the sense in which I said earlier that forwarding references sort of remember what they are bound to.
Question. In one of your slides, you had 3 different types of variable initializations with an assignment operator, with parentheses, and with braces. Can you describe advantages or disadvantages to each of those types?
Yeah, so here, so the brace initialization, I think, is probably the one I would say is most distinct there, because when you use the brace initialization, so in this case here, there is with an int, there's one primary difference, which is that the braces prohibit narrowing conversions, whereas the other 2 would not. So if I tried to write 42.5 there, the first 2 lines would compile just fine, maybe with a warning, whereas the 3rd line would be required to give me an explicit error, because I'd be doing a conversion that discards information there. In the case, this doesn't come up in the case of an int, but if I were declaring something like a vector, the braces are also assumed to mean initializer list, to be creating an saying that the vector should be initialized with this collection of values, whereas using the parenthesis in that situation would be taken to mean call a constructor that takes a single parameter of this type. An initializer list is still a single parameter, but it would be assumed to mean initializer list of one element in the case of the braces. As far as differentiating between the top 2 go, the main distinction I can think of is if there were a conversion involved there. If we were talking about, it doesn't really apply for ints, but if we were talking about a class type with a converting constructor, if the conversion were declared explicit, only the 2nd line there would be permitted. I think we are out of time, so I'm happy to continue taking questions out in the hall after this, but I need to make room for the next speaker. So thank you for coming. Hope you guys found it useful.